welcome everyone to the AMS Colloquium lecture series. I am Ruth Charney, president of the American Mathematical Society, and I will be moderating this session. Before we get started, let me note that these plenary lectures are in webinar format. That means that only the speaker and moderators can be seen or heard. We may have some time for questions at the end of the talk, so if you do have a question for the speaker, please use the Q&A button on your Zoom screen, not the chat. I will be taking questions from the Q&A at the end of the talk. All right, so let's get started. The AMS Colloquium lectures were initiated in 1896, just 2 years after the founding of the American Mathematical Society. They consist of a series of 3 lectures given each year at the JMM, designed to give a broad overview of important recent developments in the field. It's a great pleasure to introduce this year's colloquium speaker, Karen Smith, the William Fulton Distinguished University Professor of Mathematics at the University of Michigan. She received her PhD from the University of Michigan in 1993, then held an NSF postdoctoral fellowship, followed by an assistant professor position at MIT until 1997, when she returned to the University of Michigan. Professor Smith's research lies at the interface of commutative algebra and algebraic geometry and draws on synergies between these two fields. Her work in this area is well known and has earned her numerous awards. She was awarded the AMS Ruth Little Satter Prize in 2001 and was named a Fellow of the AMS in 2016. In addition to her own research, Karen Smith has had 20 PhD students and currently has 30 mathematical descendants. She has served as an inspiring role model for many women in the field. The story of her mathematical life is quite fascinating and has been featured in multiple articles and publications, including an interview in the August 2017 notices of the AMS. I urge you to take a look at that. This series of colloquium talks will focus on understanding and measuring singularities in algebraic geometry. Today's talk is entitled Resolutions of Singularities and Rational Singularities. Please welcome Professor Karen Smith.
Thank you, Ruth, for that very generous introduction. It's a great honor to be speaking in the AMS Colloquium. I'm going to go ahead and share my screen so everyone can see my slides. Are they visible? Okay, yeah. Thank you. Okay, so as you heard, I'm going to be talking about singularities in algebraic geometry. So I want to try to explain some of these pictures down here at the bottom of my screen. All of these beautiful pictures with the black backgrounds are from Herwig-Hauser's Gallery of Algebraic Surfaces. It's a great place to look and see some beautiful algebraic varieties. So I urge you to take a look at that sometime. Most of the other sketches in here are from my own book or something I made on GeoGebra, and not nearly as nice as Herwig's. So let's talk about what algebraic geometry is. We've all done algebraic geometry since high school or even maybe middle school, because we study the geometric shapes defined by polynomials. So on this slide, you'll see 3 different types of algebraic varieties that you might have seen before you even got to college, including this polar flower here that you probably would have used polar coordinates to graph, but it also happens to be given by the polynomial that you see down here at the bottom of the screen. So more formally, an algebraic variety is a zero set or common zero set of a collection of polynomials. So if the polynomials are in n variables, then the zeros of the polynomial will live in, let's say, Cn, and we'll have a geometric object sitting inside of Cn. So here I've drawn, well, actually Herwig has drawn 4 and I've drawn 1, algebraic variety. Of course, we only draw the real points because we're human, we can't see in complex 3 space. So we just draw the real points in real 3 space. Oops. No, how did that happen? Sorry about that. Each of these with the black background here is the 0 set of one polynomial. So this first one is the 0 set of x times y times z. The v stands for vanishing set. So it's the vanishing set of x, y, z. So of course, in order for x, y, z to be 0, we know that either x is 0, that would be the yz plane, y is 0, that would be the xz plane, or z is 0, that would be the xy plane. So we get this union of 3 planes. And likewise, each of these other varieties is given by just one polynomial in 3 variables, and I'm drawing the real points here. This last one with the lighter background is the 0 set, the common 0 set of 2 polynomials. I've just had, it's very difficult, obviously, for humans to draw these or visualize these things. And this is almost the best I can do to show you what it might look like if we have more than one equation in a way that I myself could actually draw. So as you see, even though I've only taken one polynomial or maybe 2 simple polynomials in 3 variables, these are quite diverse, different shapes. This green cooling tower here is what we call a smooth variety. It has no places where it crosses itself, like this purple one here is crossing itself. That would be called a singularity. It has no pinching or bending. That's a nice smooth variety. So, so these are the objects that we want to understand, and especially we want to understand those singularities. So throughout the talk, I'm always going to be talking about varieties, and sometimes secretly, I'm thinking about compact varieties, so compactifications of these things. Every variety in CN has a natural compactification in projective n space for experts who are worried about different details, but it's not too important for most people to know specifically what that means right now. So why am I talking about C and not R? Well, the reason is that when you're looking at the zeros of polynomials, you naturally want to look at the zeros of polynomials of the complex numbers. We wouldn't want to say that the 0 set of x squared plus 1 is empty. We would want to say that there are 2 zeros to x squared plus 1, I or minus I. So of course we could later study the real points of a variety, but just naturally speaking, a variety lives over an algebraically closed field, a field in which all the zeros of polynomials are seen. The second example is similar, and it may be a little bit more interesting. If we think about the variety defined by x squared plus y squared equals 0, the 0 set of x squared plus y squared, if we restricted ourselves to R, we would only see the origin. But that's, of course, a tiny part of the story. This polynomial factors, x squared plus y squared factors into 2 linear factors over the complex numbers. And if I look at the 0 set of a product, I'm basically looking where one or the other of these vanishes. So that's a union of 2 lines. There are 2 complex lines, one with slope I and one with slope minus I, and they're intersecting at the origin, which is the only real point on this complex variety of dimension 1. All right, so it's important to realize that you can really do algebraic geometry over any field, just like you can do linear algebra over any field. So in linear algebra, we study the zeros of linear equations or systems of linear equations, the common 0 set of a collection of degree 1 equations, such as this system here of 2 linear equations and 3 unknowns. That's a special case of an algebraic variety where the polynomials happen to all have degree 1. And its 0 set, the common vanishing set of these 2 linear polynomials, is a one-dimensional vector space, but as an algebraic geometer, I would call it a complex line, or more often maybe just a line, knowing that we're always thinking over the complex numbers. And this is an important point I want to emphasize so people don't get confused about dimension. This complex line, or this one-dimensional complex vector space, if I think of it as a real vector space, of course, it's So as a real object, it's two-dimensional. So when I use the word one dimension, I'm always thinking of complex dimension. So in general, algebraic geometry can be done over any field, just like linear algebra can be done over any field. And soon we're going to be especially interested in fields of characteristic P. And I'll say more about what that means soon, but I think everybody is familiar with, for example, a finite field of P elements. That's what I mean by FP. Or because again, we like algebraically closed fields, so we can see all the zeros of our polynomials. This bar means the algebraic closure of FP. And algebraic geometry can be done over any field at all, not just the complex numbers. So keep that in mind, even though all the pictures I draw will be pictures of real points on complex varieties, we can do this over any field. All right. So just very quickly, I want to point out, I study algebraic geometry intrinsically because I think it's beautiful. I'm not studying any particular applications, but algebraic geometry comes up absolutely everywhere. Varieties are everywhere in mathematics, in science, in applications, in engineering, in medicine, in entertainment, including, for example, some Pixar movies. They're everywhere. And here I just put a couple of different places where they come up, and maybe I will emphasize again this compact Riemann surface, which many people know, that's a one-dimensional complex manifold. That's always what I would call an algebraic curve. It's one-dimensional algebraic variety over the complex numbers. Every Riemann surface is. So every compact Riemann surface is. So this is a just one case where we see algebraic geometry coming up in other branches of math. And there's many, many other places. The other reason I highlighted geomathematics is kind of a shout out to one of my colleagues. I've been on sabbatical at the University of Jyväskylä in Finland, and Jonas Ilmavirta there does physics, mathematical physics, and studies the Earth, and came to ask me a bunch of questions about algebraic geometry because something he was studying about earthquakes naturally led to an algebraic variety. And it was interesting because it was a singular algebraic variety, and there I could help him a little bit. So these are just some of the places, including art, where algebraic varieties come up. We're just going to be talking about it from a purely theoretical perspective, but it's good to know that they're everywhere. Okay, so let's get into talking about smooth, or another word for smooth is non-singular complex varieties. So a smooth variety over the complex numbers is a manifold, a complex manifold. So I'm not going to rigorously define what that means. I think everybody has a feeling for what smoothness means. In this top line of varieties, these are all varieties. They're all defined by zeros of polynomials, one polynomial and three variables. Of course, we're only drawing the real points here. And these ones are all smooth. There's no pinching or folding as there are in these ones at the bottom. These ones at the bottom are not smooth. And let's just look at how rich the different kinds of singularities could be. And this is a tiny sampling, but we see we could have isolated singularities. Like in this first one, we have 3 isolated singularities, or sort of pinch points. And in this variety, we have just one isolated singularity. Here on this apple looking thing, we have a singularity where it's kind of poking into itself. In this interesting looking thing, we have a singularity which is consisting of the 2 axes coming together. This is drawn in R3, of course, and these are the x and the y axis in the z plane. I'm not telling you the polynomials here, but these are all given by one pretty simple polynomial in 3 variables. These are the real points of a complex variety. So let's define, at least a little bit loosely, what I mean by smoothness. So this is a little bit dense and you don't have to absorb all of it, but I want to point out that just what a smooth point means from an algebraic geometry point of view, which makes perfect sense also from like a Calc 3 point of view, is a smooth point is just a point where you can define a well-defined tangent space. So just looking at this cone, which you've probably seen if you've taught multivariable calculus recently. It's the zero set of this nice simple polynomial, and its gradient at each point is a vector pointing perpendicular to the cone. So so everything, as long as that gradient is non-zero, right, then there's going to be a plane of perpendicular vectors to that gradient, and that's going to be my tangent plane. So there's a well-defined tangent space at each point of this cone at every point where this gradient is non-vanishing. In other words, this cone is smooth at all points except where all the partials vanish. So the reason I'm pointing this out to you is so you can see that the singular set, the set of non-smooth points on a variety, is itself a variety. And it's not completely trivial, but it's not that hard to prove that it's a proper subvariety. It's always a much smaller set than the original variety, but it can be larger than just a point. And here we see this in this other example, where you could write down the derivatives and compute the singular set if you wanted to of this, and you would see, like I said, it's the X and Y axis. Another reason for me to point this out is I want to emphasize to you that smoothness makes sense over any field. So as every Calculus 1 student knows, you don't need deltas and epsilons to take the derivative of a polynomial, right? We can define derivatives for polynomials, and we can do it rigorously in algebra over any field. And when you can define a derivative of a polynomial, you can define the smooth locus, and all these same things will work. And we're not going to need that right now a whole lot, but I do want to point out that everything in algebraic geometry can be done over any field, including talking about smoothness or non-smoothness and singularities. Okay. So here's what the subject of my talks are. There's 3 talks, and they're all about singularities of algebraic varieties. So you're going to be seeing these kinds of shapes over and over again. And in my first talk, I want to answer essentially the first 2 of these questions on this list. The first one is, given an algebraic variety with some singularities, is there some procedure, some surgery we can do to make the variety smooth? So with the union of the 3 planes, it's very easy to envision that we could just kind of lift them apart, separate them apart, and that would be a variety almost the same as this one, but different exactly on the singular set. And that's the process of resolution of singularities I want to talk about today. I also want to point out that some singularities are sort of negligible from a lot of the things that we want to do in algebraic geometry. And that's one of the things we're going to talk about today. In my next talk, I want to get into quantifying how singularities are, how we might do that. And in the third talk, I want to talk about what is the most singular singularity. Is there a most singular singularity, and what are its features if there are? Okay, so let's move ahead with, now why is this not advancing? There we go. Okay, so let's talk about what it is to resolve singularities. So for this, you don't have to read everything on the slide necessarily. This is so much easier in person because I can gesture and move around more. But if you look at this variety V I've drawn in the plane, so this, I'm going to call it an alpha curve because it's sort of an alpha type curve. Its equation is right here, but it's not that important right now, but it is the zero set of 1 polynomial and 2 variables. And I've drawn the real points here in the real plane. So you can picture that as a piece of wire in the plane. And then you can think about just lifting that wire into 3D and getting a curved piece of wire that can be sort of smashed down to the plane exactly onto our alpha curve wire. This curve B in the 3 space is our resolution of singularities of the wire. So B here is not in the plane anymore. It's in 3D. And it's given by these 2 equations. Again, not that important, but it is a variety. It's given the zero set of polynomials. So the formal definition of a resolution of singularities is it's a smooth variety, in this case B, together with a proper map. So this is a map that's projecting down onto V surjectively, and it's proper. So the preimage of a compact set is compact, and it's one-to-one or an isomorphism over the smooth locus of V. So V has, most of its points are smooth, right? There's just that one singular point. And B and V are in one-to-one correspondence under this projection at all those smooth points of V. It's only the origin, in this case, the singular point of V, that has 2 points above it. So that's a resolution of singularities. And notice it's given from projection from a curve in a higher dimensional space. So here's the $1 million question. Actually, it isn't a $1 million question. It might have been if it hadn't been solved in earlier. But here, oops, where did this go here? Okay. Does every variety admit a resolution of singularities in this way? Does every one of these varieties I've drawn on this picture, I've copied from Herwig's gallery, does every single one of them have a smooth variety that looks just like it except at the singular set? So some variety would be some surface embedded in some higher dimensional space, probably, that's mapping surjectively onto our variety and is nice and smooth and isomorphic to our variety, except all of the over all the points that are singular. And like I said, it might be easy to imagine how to do that for the this union of 3 planes, but it's not so easy to imagine how you might do it for all these other varieties here. And it's also really important to realize when I'm talking about this, that this is an extremely small set of varieties, even though they look pretty diverse, they're pretty different. These are just one variable, these are just one equation and 3 variables, pretty low degree equations too. These polynomials are, I think nothing here is more than degree 6. And the singularities are simple, right? I mostly just have points. I have singular points here or singular lines, but in general, the singular set of a variety could be a variety itself of any dimension with its own singularities. So there could be, for example, a 17-dimensional variety living in 25-dimensional space, cut out by 50 equations, polynomials of very high degrees maybe, which has a singular set, which is itself a 13 variety, a 13-dimensional variety. And that singular set itself as a variety has its own singular set and so on. It can be incredibly complicated. So singularities are very complicated. And this is a very small set to indicate how they can look. All right, so that hopefully gears you up to appreciate my favorite theorem in mathematics. It's a Fields Medal winning theorem by Hironaka. And what Hironaka proved is that every complex variety, no matter how singular it is, no matter how big or complicated the singular set is, no matter what dimension it's in, no matter how many equations it's defined by, every complex variety admits a resolution of singularities. So there's a smooth variety in a higher dimensional space that projects onto our variety, the singular variety. It's actually a projection from a higher dimensional space onto our variety. And this is an isomorphism everywhere. It doesn't, it's a bijection between the smooth set and the resolution. So in this picture, and again, this is a very simple example that we can draw. Our cone has this isolated singularity. We already talked about it. And its resolution, or a resolution of its singularities, is the cylinder. The cylinder here is in 3 space, and this resolution map is twisting the cylinder down to create that singularity at the vertex of the cone. So pi here, this is just an intermediate step to kind of indicate what the map is doing. That's the singularity. I mean, that's the resolution of singularities. Now that is not technically a projection, but that's because I've embedded my cylinder into 3 space. If I had embedded it into 5 space in a particular way, I could project it onto the cone. And it's only when I try to force it into 3 spaces I've done here that it's no longer a projection, literal projection from a higher dimensional space. It is still a projection in a certain algebraic geometry sense. So this amazing theorem, which has been proven, more than 50 years ago now, has been open for varieties of characteristic P. So remember, we talked about over characteristic P, we can still define varieties, we can still define singular ones and their singular sets. And people have been looking for a long time to try to prove resolution of singularities in characteristic P. For low dimensional, it's been known for a while, not too long ago in dimension 3, I believe by Dale Kukowski. But in general, in characteristic P, this is an open question. All right. So given that every variety can be more or less approximated by a smooth variety, this leads us to think about trying to understand the singularities by comparing a singular variety with a resolution of singularities. So one of the things we can do is observe that Hironaka Hironaka's theorem is even better than what I stated. Not only is there a variety that's projecting onto our singular variety, but the preimage of the singular set of our variety will be especially nice. It will be a finite union of smooth varieties. So for example, we already saw the alpha curve when we did its resolution of singularities. We wound up with 2 points that map down to the singular point. So the preimage of the singular point is a union of two points. So it's a union of 2 smooth varieties. The point is a smooth variety. And also for the cone, the preimage of the vertex of the cone, the singular set, is this nice circle on the cylinder here. Now, let me just point out that's not actually a circle because, of course, I'm only drawing the real points. The preimage, this cone, if I think of it as being in C3, one equation in C3, it's actually a 2-dimensional complex variety. So it's a 4-dimensional real variety. Its preimage of this point here is a 1-dimensional complex variety. This is a Riemann sphere. And what you're seeing, this circle is the real axis in the Riemann sphere. The real axis in the Riemann sphere is a line that comes back to itself at infinity. And that's that circle you're seeing. So that's what is the exceptional set, is the preimage of the singular set. And that's an important way to try to understand the singularities itself, try to classify or understand the singularities, is to understand how many components are in the singular set and what are their topologies, for example. And a more complicated singularity will have, we expect it to have many more of these components, and maybe they have higher genus, or maybe they're making a necklace of some sort. There's going to be a much more complicated exceptional set for a much more complicated singularity. Okay, so looking now at a class of singularities called rational singularities, defined by Michael Artin, who's one of my mathematical heroes. So I've put a lot of my mathematical heroes and friends on my slides, and Michael Artin is one of them, who was a mentor for me when I was at MIT. He defined a class of varieties called rational singularities that are almost smooth in a certain sense, so that when we want to do some kind of a geometric or analytic procedure on them, we can pretend that they're smooth. So in blue on the slides, I've put in some precise definitions. You don't need to read them. They're just for experts. Let me just say, for non-experts, roughly speaking, a rational singularity, if we just focus on surfaces, means that the preimage of the singular set is just a union of Riemann spheres. They intersect transversely, so none of them are tangent to any other, and they're making a tree. They don't have any kind of topology where they come wrap around and make a necklace or some more complicated object. Just a tree of complex Riemann surfaces. So that's what a rational singularity is. And the reason these are important is because they basically tell us that we can approximate our singular variety by a smooth one. In some sense, a resolution of singularities is always an approximation of a variety by a smooth one. But when I have a rational singularity, it's especially good approximation. differential forms behave well, passing from one to the other and so forth. And so it's kind of an important area in algebraic geometry, a small little niche area, but an interesting area of trying to identify when varieties have rational singularities. Or sometimes a mathematician may be working on a problem, not in algebraic geometry, and they run into a variety, maybe a parameter space for something they're working on happens to be a variety. They'd like to apply some tools from analysis, and they could only apply tools from analysis if the variety is smooth. Well, they'd be stuck if they have singularities, but sometimes if they have rational singularities, these obstacles can be overcome. So rational singularities are really important for this reason. So how do we identify them? On this slide, I just put a bunch of places where varieties came up and people needed to know if they were rational singularities or not. I'm not going to read them all because you can see them, and these are from different, more or less different areas of math. All four of the topics in blue, Schubert varieties, moduli spaces of vector bundles on Riemann surfaces, cluster varieties, all of these things are in blue because they're all proved using kind of a similar method that I want to talk about now. There's also a very recent preprint I noticed on the archive this year where some mathematicians proved that some nested Hilbert schemes of points on a smooth surface is also a rational singularity. So you can see, even though this goes back to 1985, my list at least goes back to 1985, people are still using, looking at varieties are coming up, and we need to know if they have rational singularities or not. Let me just say something about the people. So I've got my two colleagues here, Thomas Lamb and David Spire, and I'm sorry I didn't put their names under the pictures. That's an oversight. And they are both essentially combinatorialists. They were studying some Richardson varieties that came up in representation theory from a combinatorial point of view, prove that they have rational singularities. And then these four people, actually there's three people, because Greg Muller here has a dual life as a roller derby referee, and I like that picture, so I put it there. But then I also wanted to show you his face. So we've got two pictures of Greg, and then we've got Angelica Benito and Jenna Reichko. All of these three people here were former postdocs at Michigan, and we worked together to show cluster varieties, which are a kind of thing that comes up in combinatorics, have rational singularities, at least most of the time, for a large class of them, finitely generated ones. Okay, so what is the technique for, or the strategy for attacking this problem, or one strategy for attacking this problem? So one strategy for attacking this problem is to, like most problems in algebraic geometry, or many problems in algebraic geometry, we can reduce the problem to an algebraic problem. So we take the geometric problem of whether or not our resolution of singularities has a particularly nice form, and we reduce it to an algebraic problem. And I'm going to explain how to do that on the next slide. But then the interesting step here is that algebraic problem can be solved often by reduction to characteristic P. So I will explain that as well. But gosh, this is a place I'd really like to stop and ask for questions. It's hard to give a talk on Zoom and have no idea if people are following me. But this is kind of the strategy that's used in many cases to prove rational singularities. Not always. That recent preprint I mentioned, I don't believe use this particular strategy, but there are also more recent papers that do. Okay, so to understand how this works, I need to take you through a crash course, first semester algebraic geometry. So let me introduce this coordinate ring. So I'm going to take my varieties. So remember, V, my variety, is just a zero set of polynomials. It's living in Cn, complex n space. So if I have a polynomial function on Cn, just an ordinary polynomial and n variables, I can restrict it to V. And now I have a function on V. I call that a polynomial function on V. So I look at all such functions on V, all polynomial functions on V. This is called the coordinate ring of the variety. This is a really important variety in ring in algebraic geometry. This coordinate ring is a finitely generated C algebra. It's finitely generated by the coordinate functionals. In other words, just the functions that take a point in Cn to the value of the ith coordinate. That's the xi, the ith coordinate functional. And every polynomial is just some C algebra combination of those. So the coordinate ring is a finitely generated algebra, and it's associated to the variety V. And here I give you an example. If we take that cone, our favorite cone that we keep looking at, the coordinate ring, because this lives in R3, or sorry, C3, we're thinking about these in complex space. The coordinate ring is going to be generated by the coordinates x, y, and z, the coordinate functionals, but there's a relation because x squared plus y squared minus z squared, that polynomial vanishes everywhere on the cone. And so any polynomial that's a multiple of that one will also vanish. And in fact, that generates the ideal of relations on this algebra. So that's the coordinate ring. It's a pretty simple thing, and it's something you learn on almost the very first day of a class in algebraic geometry. And then throughout the semester in algebraic geometry, we would learn that the geometry of the variety and the algebra of the coordinate ring are intimately related. Essentially, they're the same thing. A very fancy way to say it, there's an equivalence of categories between varieties and algebras. So what I mean is that every variety in Cn will give me a finitely generated C algebra. And every C algebra, every finitely generated C algebra will give me a variety. And not only that, but a map of varieties. So for me, a map of varieties is a map given by polynomials in the coordinates. That's what we mean in algebraic geometry. When we talk about a map of varieties, that will always correspond to a C algebra map. And conversely, a C algebra map will always give rise to a map of the corresponding varieties. So geometric features like a point in V. A point in V corresponds to a maximal ideal in this ring. That's the famous Hilbert-Snow-Stillen set. So now it's a 120-year-old theorem. And different features, like whether or not V has different components. Does it have just one irreducible component, or is it a union of some other components? That corresponds to the property that the ring is a domain, an integral domain. There's only one component if and only if the ring is a domain. So on and on and on it goes, and through algebraic geometry, you would learn more and more geometric features, how they translate into algebra, and how these things are equivalent. So for example, smoothness of a variety can be defined completely algebraically without referring to tangent planes or anything, just having to do with numbers of generators of maximal ideals. And that's a regular ring. Actually, there's many different characterizations of regularity. None of them need really a C algebra. You could do this for any kind of Noetherian ring. So the question we're at here is, well, if I want to understand algebraically, what does it mean that the singularities of V are rational? What can I do? What can I do? What's the algebraic correspondence for that? So here's where we get into the reduction of characteristic P. And just very quickly in blue, red, or whatever color that is, purple down at the bottom, I've tried to say this slightly more formally, but for non-experts, for colloquium, for relaxed talk, just what we can think about is if I want to study the cone or some other variety, I can look at it instead its coordinate ring. And when I look at its coordinate ring, I notice I have, some generators and relations. And it really doesn't matter what the field C is here. I could study this same ring with the same generators and relations only over FP, a finite field of P elements. And there's a whole theory that can be made very rigorous, and I'm hinting at that in the red down below, which says that if I want to study this coordinate ring, if I want to study this variety, and instead study the coordinate ring, I can study that coordinate ring by studying these mod P reductions, or these characteristic P models of the ring. So for example, my ring is going to be regular for large P if and only if my variety is smooth. And that is not the case here because we see we have a singularity. Okay, so why would I want to reduce to mod P? I mean, if there are analysts or differential geometers in the audience, they're surely thinking that was crazy. Now we got rid of integrals and vector fields and differentiation and epsilon neighborhoods and all the good stuff of analysis. Yes, we did, but we've got a new tool which is really powerful instead. And that new tool is this beautiful fact I've got here. Sometimes I call it the freshman dream. I'm not the only one who goes the freshman dream. I guess I got that from somewhere. I've heard it repeated. So let's remember what it means to have characteristic P. A ring has characteristic P means that if I take the number 1, you know, the unit element, the one element in the ring, and I add it to itself P times, a ring I can add, I get back to 0. And if I have a ring of characteristic P, such as, for example, a field of 11 elements has characteristic 11, polynomial ring over a field of 11 elements has characteristic 11. If I have a ring of characteristic 11, when I take F plus G to the 11, I'm going to get F to the 11 plus G to the 11. Every freshman calculus student knows how much this simplifies arguments and how powerful a tool that is, right? This might be wrong in freshman calculus, but it's right in characteristic P. And this is a really, really powerful thing. And it's very simple. It's just because the binomial coefficients are all divisible by P when you expand this out using the binomial theorem. So because we have the freshman dream, the Pth power map, where we're raising things to the Pth power, the Pth power map will be a ring homomorphism. So it will be a map from R to itself that both preserves the multiplication. Here I'm assuming my ring is commutative, as all coordinate rings of varieties are. And it will, that's always true for any commutative ring, that the Pth power map would preserve the multiplication, but preserving the addition is the special thing to characteristic P, and that makes this a ring homomorphism. Both multiplication and addition are preserved, ring homomorphism. So this is a tool. Now I can iterate this map. When I iterate this map, I can think of it as a dynamical system. I can follow the process, what happens to different elements. And what's especially nice is for most rings, rings that have no nilpotent elements, as our coordinate rings never will. Our coordinate rings will always be of that type. The set of Pth powers will form a subring, which is isomorphic to the ring. So when I take the Pth power map, the image will be R to the P, the kernel will be 0 if I have no nilpotents, so that will be an isomorphism of rings. So what I get is, I get this infinite chain of isomorphic subrings. And I like to think of this as kind of a microscope. If I imagine R being a singularity, so it's the coordinate ring of a singularity, and I'm focusing in on a singular point, and I'm raising to the Pth power, I'm going deeper and deeper into the ring, looking closer and closer at that singularity. This is what we get when we go to characteristic P and we give up all those good tools for analysis. We get this Frobenius map. All right, so let's talk about how to use that. I already hinted at this earlier, how to use that Frobenius map to check a variety is smooth. Now, this is not actually usually done, and especially not for this cone, which we can easily see is not smooth. But I wanted to put it here as an example that smoothness of varieties, again, corresponds to a property of rings called regularity. And so if I have a ring of characteristic P, it will be regular if and only if this Frobenius map has a special algebraic property called flatness. And that's a technical thing. If you're not an algebraist, it doesn't matter too much what it is. I did kind of describe it down here in blue below for people who are curious. But the point is that there is a way to characterize when a ring of characteristic P is regular or is corresponding to a smooth variety. And it's very special to characteristic P because we only have this Frobenius map, this Pth power map. This F here is the Pth power map. And that's only makes sense in characteristic P. So a very famous theorem of Ernst Kuntz says that we can check a ring is regular if and only if the Frobenius map is flat. And so, this is just kind of an example to indicate how reduction to characteristic P works. we can show this cone is not smooth by showing that the Frobenius map fails to be flat when P is large in these characteristic P models of our coordinate ring. Again, that's not the best way to show it. It's just one example to show what it could do. But now we're going to get into showing or thinking about how we might show a variety has rational singularities. And we're going to do a similar thing. So if we want to show we have rational singularities, remember rational singularities is something close to smooth. It's like a negligible singularity somehow, that thing that Michael Artin defined, the rational singularities. So we'd like to think about what almost smoothness could mean in characteristic P. So Hoekstra and Hoeneke, again, some of my math heroes, they defined a concept called F regularity, or strong F regularity for experts, which roughly means that we have a ring where Frobenius is not flat, but it's kind of almost flat asymptotically after we iterate the Frobenius map enough. And here I put down two different definitions, neither of which you need to know to appreciate the talk, but I wanted to give you a precise definition so you could just kind of see what's involved. And so for more algebraically inclined people would have a precise definition. But the point is here that we can, this property, F regularity, is very close to being regular, very close to being a property that a coordinate ring of a smooth variety would have. And so that's what we're going to try to use to characterize rational singularities. So here is a theorem. And this is actually the theorem that we use to prove with Angelica and Greg and Jenna the theorem about cluster algebras, and it's closely related to some of the other theorems on that list. So if I have a variety, and this means a complex variety, if I have a complex variety and I know that all of its mod P reductions for large P are F regular, they have this property introduced by Hoekstra and Hoeneke, then that variety will have to have rational singularities. So might be hard to believe for non-experts out there, but this is actually much easier to check than going through and trying to find a resolution of singularities. So we didn't get into details that much about how to find a resolution of singularities, but in practice, it's very hard to find one. And even if we could find a resolution of singularities, Hironaka's theorem says a resolution of singularities exists, but it doesn't really tell us how to find it. But even if we could find it, it's not easy to tell whether or not it has the properties needed to show that the variety we started with has rational singularities. So this is actually much more practical because this F regularity property can be checked. And in fact, it's essentially equivalent to having rational singularities. It's a technical difference. There's a concept called F rationality, which is similar to F regularity, and that's literally the same as rational singularities, meaning rational singularities over the complex numbers is the same as almost all mod P reductions being F rational. For example, I stated it here somewhat more carefully for a hypersurface. If I have a variety in Cn defined by one polynomial, and for simplicity, let's say all the coefficients are integers, so you know exactly what I mean by mod P reduction, then that variety will have rational singularities if and only if, when I reduce mod P for large P, I have an F regular ring. And that's that thing defined by Hoekstra and Hoeneke, which is close to being regular. All right, so this procedure is a tiny piece of the story that I just told you. The Frobenius map is used to understand singularities in much bigger ways since that little story about rational singularities happened. And many of the singularities in the minimal model program in algebraic geometry, for example, have been characterized using that Frobenius map, that P-power map, including log terminal singularities and log canonical singularities and Dubois singularities, all these things that you see on this page, which you might have heard of, or seen advertised in seminars. If you're not an algebraic geometer, you might have noticed it in an abstract. These are important pieces of the minimal model program, which is a program for classifying complex algebraic varieties over any field up to almost everywhere. Isomorphism, and these all come up in there. And down here, I've put some pictures of some of my friends and colleagues who have worked on these things. For example, the Dubois singularities is Carl Schwede's thing, and Mircea Mustada here, who's my colleague at Michigan, has worked on various aspects of all of these things, and Kevin Tucker as well. So those are, vast stories to be told at a later time, not in my second talk. I'm going to switch gears, but I just wanted to point out this technique of trying to understand a complex singularity by reduction to characteristic P and iterating the Frobenius map, the Pth power map, is used in many places in algebraic geometry. So I think that's when I'm supposed to stop, because I know people may have questions.
Great, thank you very, very much. That was absolutely fantastic. If I was early in my career, I'd be tempted to go into algebraic geometry. We do have a few questions in the Q&A. So
let me see if I can. Should I stop sharing my screen?
Oh, no, you can leave them on if you want. I think they're not too complicated.
Okay.
I think I can read them to you. So the first question I think is interesting. It says, "What is the origin of the name variety?"
Oh gosh. So I guess it's coming from French, and I don't really speak French, and I do not know. So I'm very sorry, I don't know. Yeah, it's an interesting question.
Okay. I'm gonna look it up. The second question asks, how does the resolution of singularities differ from the blowout of a singular point?
Oh, that's an excellent question. It essentially does not. Let me go all the way back to some of these pictures. In fact, how would you prove a resolution of singularities? Or how did Hironaka prove it? What you do is you blow up points. So I think the question is asking about blowing up. But yeah, it's so, for example, what blowing up means is if I'm looking at my cone here, can you guys still see my screen?
Yes.
Okay, so blowing up means I replace a point. So if I blow up the origin, I'm going to replace the origin by, it's like a surgery in topology, by all the lines on the variety passing through the origin. And when I do that, I replace the origin by all the lines through the origin. This is exactly what happens. I get a circle of lines, right? There's a circle of lines, and that's what's happening. And that is a blow up. This resolution of singularities is the blow up of that one point. And it resolves the singularities. In general, when we have a more complicated variety, you can't just blow up one point. You may not even be able to blow up just a point or a sequence of points. You may have to blow up curves and higher dimensional things, and it's very complicated. But essentially what Hironaka does is he gives a way to choose a sequence of subvarieties to blow up and prove that eventually going through the procedure of blowing up those will resolve all the singularities. So he has to define some kind of invariant that improves when you do some kind of blow up. And that's exactly what he does. So that's a good question. This is very closely related to blowing up.
Okay, here's another interesting question. Is the resolution Hironaka gives essentially unique?
That's an excellent question. And the answer is definitely no. Mm-hmm. So actually, this is what the minimal model program is about. Even just looking at this cone, this is the most obvious resolution of singularities, but I could then go and blow up a point in the exceptional. So on this circle here, I could blow that point up. And if I blew up another point on that cylinder, I would get a new smooth variety which would have not just that one circle there, which is actually a Riemann sphere, but another Riemann sphere. So it would have two complex lines, and it would all collapse back down to this thing. So there's infinitely many resolutions, and there's not a unique one. I mean, Hironaka does give us a procedure to come up with a particular one, but there's nothing unique about a resolution of singularities. Now, you might also ask the question, among all the resolutions of singularities, is there somehow a minimal one or a most canonical one that all the other ones map to somehow? And that's what the minimal model program is about. It's about when you have a class of smooth varieties that are equivalent to each other in this sense, that they're all isomorphic to each other except on some subvarieties. You want to try to find one that they all map to, or maybe one that's as small as possible. That's what the minimal model program is about. Yeah, and there isn't one. That the answer is that there won't be a smooth one. In the minimal model program in dimension 3 and higher, we're forced into dealing with singular varieties. The minimal thing is singular. It's rational singularity. It's like the things that's like the last slide I was talking about. Those singularities we need are those come up in the minimal model program exactly to get that uniqueness or something close to uniqueness. It's an excellent question.
Wait, another question just popped up by the same person. So if, oh, this is a follow-up question. So if a variety has a rational resolution, then will Hironaka's procedure find it?
The rationality of it doesn't matter. So if one of them is I assume what the question means is that, let me go to the definition of rational singularities. Oops. The definition is independent of the resolution of singularities. So any resolution will, if I have a rationally singular surface, all the resolutions will have the property that the exceptional set is a union of Riemann spheres intersecting transversely, forming a tree. So yes, Hironaka's theorem will find it because they all will have that property. This definition does not depend on the resolution. It's an excellent question because the way I wrote it looks like you might have to make a choice of a resolution. All of them will work.
All right, I think that's all the questions we have. Let me remind everybody that we have 2 more lectures in this series, same time tomorrow and Friday. So come back.
And I wanted to emphasize also that I'm planning to keep them somewhat independent. So you can bring friends, or you can, if you got lost in something, it's not a big deal. I'm going to start over from the basics at the beginning and try to explain it again. If they do build on each other in some sense, but they're not completely independent. But there's not going to be like a prerequisite to have attended this lecture and understood it.
All right. Well, thank you for a fantastic lecture.